What I'm going to keep going is continue to talk about that every distributions we're going to encounter, you can consider that you can review that through the kind of like simulation, event way, or you can say that mathematically, how can I build a mountain, and then use that mountain to generate a transfer function. And both things we're going to be used later on, okay? And let me go Google what is that term's going to call, okay? It's called CVAR, and that's the most important term we're going to use again and again in this class, okay? And to build a CVAR, let me see if I can find a good example. Not here. Okay. Every distributions, okay, is a mountain. So you see a mountain down here? Okay, this is in your slide. And of course, that mountain is going to be getting uglier and uglier. What I mean is that this mountain is not a bell shape you're familiar with. Agree? But why we have this kind of strange mountain? Because usually we're talking about survival. So the survival means what? There's an aging process of something that getting less and less likely. So whenever you have this, okay, so see the blue region here is called value at risk. So that value at risk is almost like your p-value when you deal with statistics. Your p-value is what? 0.05. And here what we're saying is that, oh, if I'm only have 5% of chance to survive, then looking at the CDF, which is this transfer function from 0 to 1, and if I cut my blue at that point, okay, we call that beta function, and how much the red region left, given I cut a certain blue point. And what do I mean by that? What kind of car you're driving right now? What kind of car you're driving? Okay, so what I'm trying to say is that, okay, let's assume that car is 10 years old, or maybe older. How old is your car? Don't worry. I was a student before. I had a pretty old car before. Okay, so for a 10 years old car, okay, do you change oil all the time, or you change oil? How often you change your oil? When the light turns off. That's a good point. So let's just say that you change oil every 6 months. That's about right? 5 months, a little short. Okay, and then, so if you don't change oil, how likely you think the car gonna kaput next day? Most of the cars these days are pretty reliable. As long as you don't torture it, like driving from here to LA in one shot. So you don't run the engine really, really hot for a long period of time. Probably can last a little longer, right? So the blue region is basically said, okay, how long I'm willing to wait, okay? 6 months, 6 months plus 1 week plus 2 weeks. Of course, the longer you wait, the likelihood this thing's gonna last, gonna get less and less. So first things about the blue region, why we're interested in all the mountain is that some mountain got a large tail. Some mountain got a heavy tail. Some mountain got a very, very unlikely tail. It means that, hey, if you don't do, in the old days, especially the muscle car, if you don't do something in time, the car is not going to last, okay? But in the last 20 years, most of the car reliability changed quite a bit, okay? I can also tell you the example like a jet engine. How many of you think the big jet engine technology, the shape of the blade and everything's hard to manufacture? It's not hard, okay? Anybody can copy the curvature, scan, and get that done. But in the world, how many jet engine company actually survive? Not too many. The Whitney engine and the GM and one more, Rolls-Royce, for the big engine, okay? Why is, not too many company can survive, or, how likely I can, go buy a Rolls-Royce engine, take picture of everything, 3D print, and then come up with an engine just like a Rolls-Royce engine. Very easy. But how likely I can have an engine run hours and hours? Let's say that a Rolls-Royce engine for major maintenance every 100,000 hours to open up, to check the crack, the hairlines, and everything. How many engine you think if you just copy paste you can get it done like that? It's mission impossible. You'll be lucky to run 10 hours without a crack. So in reality is that, how long you can wait. That is the blue region we're interested in, okay? And I'll give you another example. The school, North Carolina just told us, hey, for those people who want to have BA2 and BA5 shots for COVID, you can start register tomorrow, okay? I will do it tomorrow, immediately. But for some of you, 20 plus, young and healthy, how long do you think you're going to wait? You're going to wait as long as you can, right? So the first thing is about how long you're willing to wait. If you have a Rolls-Royce engine, you don't care. You can wait and wait and wait. But if you don't have you have a terrible engines, every hour, every other hour, you want to check. You have a really, really nice brand new Corvette, okay? You probably can run the car really, really hot without any worry. But if I have a beat up Toyota pickup trucks, I probably will check every other day. Do I still, if I have oil leak of my my engine, I probably will check the sticks all the time, make sure the color is right, not sticky, no smell, and I have the right level. So how long I have to check, that means that how much alpha I have, okay? And in your old days, when you try your statistics, okay, we usually set alpha at what level? For experimental design for statistics, usually alpha you set at what level? 0.05, right? And who said 0.05 is the right level? Can I have 0.10? If something I don't care, I'll do 0.10, right? 0.1, 0.1. And but if I'm talking about the next lunar missions, NASA says they want to go back to the moon, okay? And they want to check the engine. Do you think alpha level for quality control at 0.05 reasonable? Should be 0.000001, right? You don't want to have anything, it's not reliable. So your alpha level will be very, very small. So your VAR, the blue region, getting smaller and smaller, means that I have to set up at a certain level. And then what we're really interested in is what? You set it up at that level, how much residual life still there. So if I'm way too long, you might as well just forget about it. But if you try to do it too early, you're wasting a lot of resources. So in other words, is that if I have a, how old is my car? Yeah, I have a RAV4 Toyota. It's about 4 years old. Okay, I'll check. I think that's a reasonable car, but I still would check every 3 months, 4 months, but keep waiting too long, I might as well just trade in because there's nothing left. So the decision here, pay attention to our conversation. Do you think there's a human factor involved here? Means that how late is too late? So in other words, for example, when you took your statistics, when they say alpha level at 0.05, anybody tell you where's that 0.05 coming from? That 0.05 really is a convention from human factor. Why? In the old days, we asked 20 questions. So 1 of 20 is wrong, then you're not going to pass. Okay? And then, of course, people joke about it is the KGB, Soviet Union secret police approach is that if I just keep beating you, did you do it? Did you do it? And sooner or later, you'll start saying yes, 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 and surrender to it, right? So the alpha level is a human factor. How late is too late? How much is too much? That is in your heart. But at the same time, that how late is too late also relate to a physical distribution, which is through our counting process. So in other words, the shape of the mountain is going to be from our data. And right now, I'm just, our last exercise is I give you a simulation and said that, hey, I give you the chance to have something happen and how long I have to wait to see that something happen. That's where that waiting process or counting process involved in building up that distribution. Okay, so I just try to zoom out here to let you visualize why I have to torture you with few more distribution, because those shape basically gonna be the real world data. I give you a real world data, maybe from medicine, how long I have to wait, or from some mechanical maintenance schedule. And people talk about right now, what is the #1 challenge for alternative energy? A lot of time is when the wind comes, you don't have enough battery or place to store the energy. And then when sometimes you have a lot of wind, but you don't have the need to use that alternative power. So it's uncertainty of usage, uncertainty about storage, how to combine the two for better use. Okay, in some areas it's easy. Is like in West Texas or the Colorado, Rocky Mountain area. A lot of cities or county, they have the wind farm for the wind turbine, and they will say that, oh, if I have extra energy, I'll use that energy to pump water to the highland to store the water, and then at night or when nobody uses the energy, I can use that way to store what's extra needed. But when I need it, I can balance that. So sooner or later, we're not just dealing with the shape. We would like to change the shape of the distribution, but sooner or later, the game is between, okay, how much risk you're willing to take and how much you're willing to invest something in order to balance the uncertainty. Okay, so remember in the last first week's lecture, I talked about the like two friends dating problems, or the 6 people stay in the cave. We're gonna still facing similar problem. Okay, would you take the risk based on this kind of physical shape of the distributions? And what will be the VAR level? What will be the conditional of that VAR level? And then what's your alternative? Spend money, have a plan B, how to balance among this stuff. Okay, back to the distribution. Okay. Lip service on one distribution is from uniform to binomial. Okay. In binomial distributions, I only have one P is fail. I only have 2 options, right? 0 and 1, success and failure. But if I have more than 2 options, I can have, say, 0, 1, 2. That's 3 options. Or in tossing a dice, how many options I have? 1 to 6. And so now the questions is that every time I would like to know how many times. Okay, I will have 1. How many times I'll have 2? How many times I'll have 3? So the original Poisson distribution for binomial is what? Success, failure, head, tail, head, tail, head, tail. And if you have multinomial example, is that how many chances I'll have 1? How many chances I'll have 2? How many chances I'll have 3? And then the combinatorics possibility will be 1, 2, 1, 3, 3, 4, combinations. And when you combine all the combination together, that distributions is not binomial, it's multinomial distribution. And if you have multinomial distribution, like you have 3, and you can still turn this multinomial distribution into a multinomial expected value and so on. Okay? Now, and for gamma distribution, how many of you remember gamma distribution? Ever heard gamma distribution? Yeah? When did you have a gamma distribution? Was whom?
I don't remember what class it was called, but it was last semester.
Okay. And gamma distribution means avoiding eye contact? Remember? Anybody remember? When did you hear gamma distribution? I want you to not memorize it or go find Wikipedia's answer. Intuitively, what is gamma distribution? Wait time of what? Good job. In exponential distribution is what? Wait until next failure. Wait until next arrival, right? What if, okay? Wait until the arrival of what? Is what if, okay, I have one alternative. So in other words is that I have 2 bottles of water. I'll drink the first bottle whenever I feel thirsty until the water is gone. But I have a second bottle. So I'll wait until the second bottle is all gone. Then I consider, hey, I'm running out of water. So that's 2 failure. Then you consider it's a true failure. So can I have 3 bottles? I can 4 bottles. So gamma distribution in reality, what it really means is wait until the ends failure. Okay? gamma distribution, okay, there's a special case. If you guys took my DOE, I talk about chi-square distribution. And when I talk about chi-square goodness of fit, chi-square is a special case when degrees of freedom equal to 2. Okay? But here we're talking about general gamma distribution. The gamma distribution is that, okay, now if, okay, let Ti be a continuous random variable, the time between I minus 1 and I's failure, then the time from I equal to 1, I equal to 2, I equal to K. So every failure, so in other words, I can play this game by using our simulation last time. Remember, last time we have the simulation and it says that, okay, 0, 1, 0, 1 until I have one failure. So I use the time in between as my failure time, right? This time what I would do is what? The first failure doesn't count. I'll wait until the second one I consider as the failure time. Or I can use, say that, one failure is not failure, two failure is not failure, until the third failure I consider is the true failure. So the Ti, okay, is exponential. But Ti, I plus 1, from I equal to 1 to equal to 2, equal to the case 1 is the one I'm interested in, then that is a gamma distribution. So if I write this back in the exponential form, I say that, hey, I only care about the number K failure because that's the failure I'm really fail. My engine really died. The patients, can the other day I actually talked to a female doctor. She was talking about C-section and for pregnancy, and she tried to explain to me that in the old days the C-sections is limited to probably 1 or 2. Basically, the doctor would tell the mom, you can have a C-sections, but if you have a C-sections, you can only have 2 pregnancy, no more than 2. Your body not gonna recover from it, or you cannot sustain the pressure from the size of the baby. But they said modern day, because of the certain design of the surgery, it can allow more and more. So the comparison of K's failure means what? If I said that 1 minus the last failure at certain time, xk happened in 10 hours, in 100 hours. Listen to me. If I only care about the fourth failure happened after 100. So how many failure between 0 and 99.99999 before the last failure? 3, right? Because the last ones, so that's why if we want to measure, okay, the failure, I basically said that, 1 minus the last one, so look at here, the part I marked red is that you will have K minus 1 failure in between. And if you have a 1 minus 1 failure in between, the PDF, the CDF can be written in this way by taking the exponential part, because that part is consistent, only the failure from 0 to K minus 1 inside. And then if I rewrite this equation for the derivative, or find the PDF of the CDF, okay, and from I equal to 0, and then from I equal to 1 to the n minus 1. What is really important for the nth failure is that the whole equation will end up with this gamma function at the end. Okay, and gamma function is the factorial function. Okay, so for example, I think Excel now can do gamma function, gamma function. Okay, first things first, let's say gamma equal to 0. Huh? Oh, they don't allow me to use 0. Okay, gamma 1. Let me do this. So this is my gamma function. Gamma of the set of number. Okay, so anybody can tell me what is gamma function? Four is the most simple way to show what is gamma function for an integer. Gamma function is equal to, this is my k's value, okay? So gamma function is really k minus 1 factorial. So 1 minus, so if I use this as my gamma minus 1 and take factorial. Okay. See, that's exactly the same number. So gamma distribution is about k failure. K failure means that in between you have a k minus 1 possibility. Here, let me write it this way. Oh, sorry. Here's my time. Okay. And then let's just say that we're using time just like before. I don't want to give you another counting exercise because that will be too much work. Okay. So let's just say that at time 22, at time 21, I have one failure. And this failure is k equal to 5. Okay? Okay? People look at here. K's failure, there's number 5 failure at that time. So in other words, how many failure I have to arrange inside here? 4, right? So I need to assign a 1 randomly here, or here, or here, or here. But I know that the minute I decide my last failure, my number 5 failure at certain time, I have to say that, okay, I left 4 slots for you to play with, and you need to decide when to assign the first slot, second slot, third slot. That's where the gamma function coming in for the n k minus 1 factorial. Okay? And the rest of this, okay, is just simple algebra, okay? But what is important here is you need to understand why we need whenever you talk about gamma function, the gamma distribution, you need a gamma function. And why you need a gamma function is because you need a n-1 event after you decide when you're going to have your, k-1 event, whenever you decide when you're going to have your k event, okay? And if you do that, okay, and your expected value is k, one more here. What is the exponential distributions mean and standard deviation? Is lambda squared, right? Right? So guess what will be your gamma distributions? K times theta, or k times lambda squared. You follow me? Means that I'm stretching it a little bit over time, okay? And you will end up with your entropy computation here. But we'll come back for more example. I think this is just FYI. Don't worry too much about the entropy computation. Why? Because this is just mathematical yada yada. I'll give you something easy to visualize. Okay? So for gamma distribution, you must remember this. What do you need to remember? Gamma, here, number one, would you consider exponential distribution as a special case of gamma distribution? That means what? There's no failure before my first failure, right? So gamma distribution is have my case failure. If I have my case failure, inside I can have k-1 factorial to a range, okay? And if I have that in exponential distribution, my mean and my variance is lambda and lambda squared, right? Gamma distribution is k theta or k lambda and k lambda squared, okay? Next, okay, let's talk about another distribution. It's called log normal distribution. Before I do that, let me do this. Gamma distribution. Okay. Gamma distribution, look at here. K equal to 1 is the red curve. That is my special case, exponential distribution. But when my K getting bigger and bigger, they'll move closer and closer to the blue one. Okay? And what does that mean is that sooner or later, okay, it will just shift more and more like a regular mountain shape. Okay? And then the transfer function from 0 to 1, some will have very, very high speed. Well, let's do this, okay? Compare the two curves, okay? The purple one and the red one. I'm just having one is die quick, so I have the where's the purple one? Theta equal to 1 and k equal to 0.05. Okay, it dropped really quick, and the other one is the red one, drop a little slower. Or let's look at the curve here. I have a bunch of transfer function. Okay, the blue one looked like a lot shallower and the other one is the purple one. Reach 1 really, really quick. Here's the questions. I don't care you understand the geometry or the algebra anyway. But I'm just telling you that, hey, I'm giving you two engines here. One engine, the failure from 0 to 1, grow until totally fail, okay? And the time scale is from 0 to 20. One is the blue curve, the other one is the purple curve. Which engine would you like to have? Young man in the back, which engine would you like to have? This is the failure from 0 to 1, 100% failure. Which engine you think intuitively, just by looking at this two curves? You like the purple engine or you like the blue engine? There's two extreme cases. You follow me? Guess. Just tell me which one you would like to have. The blue engine, or you don't need to think about the mass, how many failure. I'm just saying that I give you two engines from 0 to 100% failure. Okay? Which one you think die quick? The purple one or the blue one? Okay, so purple one is bad case. Okay? Right now, you just think that we're going to build a bunch of mountain. Okay? So the PDF, if it's dropped really quick, or the PDF is really close to this side, you know the transfer function means what? Zoom, reaching 100% failure really quick. That's a terrible engine. Whenever you have an engine or something, it's kind of like wait and wait and wait, can wait for a long time. That is probably a better engine to have. Okay, so mathematically, we're just trying to build all kinds of curve for PDF and CDF, not through simulation, but through observation, and said, hey, what kind of engine is this? And of course, later on, the accounting will be two curve, for example. Compare blue one with purple one is easy. Compare, what about red one and black one? Which one is a better engine? Which one? Which one died quick? Red one or black one? Red one. Red is the bad one. But sooner or later, we're going to reach the cases here. Is, say, the yellow one versus the green one. Okay? The yellow one versus the green one, which one do you think is better engine? Come on. Huh? Yellow one is a better engine? Well, I'll say this, okay? If you wait after week 7 or the 7th hour, if both survive 7th hour, there's no difference. You follow me? Well, there's not much difference. It's kind of like, hey, you maybe looks healthier than me, and you have more risk than me, or I have more risk than you when we were young. So the yellow one is not as good as green one at the beginning. But sooner or later, after we reach certain points, actually, there's not much differences. But on the other hand, if you compare, for example, people look at the green one versus the black one. I just want you to make up story here. Black one versus the green one. What do you see here? Similar in the teenage, right? When they were young. Green probably died a little quicker than. Can you guys see here? Let me make it big. But not much difference, right? Right? That means that, hey, green may be a little riskier than black, but not much differences. But if I wait after 3 weeks or 4 weeks after this age, can you suddenly see that black has become bad news? Because after that, the failure is getting faster and faster. There are more failure happen. Okay? So now you see when we start playing with this gamma distribution, and we're basically said, okay, give me the data so I can figure out the k value, the theta value. Oh, what kind of average in the k, in the theta. But those parameters, we're going to use data to reflect. But the decision as a system engineer, we're really trying to figure out is that, for example, let's do this, the amber one versus the black one. At the beginning, which one is terrible news? Huh? The orange one died quick, right? But after, if they can both last, after they cross, suddenly becomes what? The black one died quicker, and the amber one died slower. So let me use another example, using epidemiology as an example. Which patients you think that got more geriatrics risk? Which patients got more pediatrics risk? You guys follow my questions? Which one, when they're young, need to see doctor all the time? The amber one, agree? The amber one, when it's young, trouble, trouble, trouble. The black one seems, no problem, no problem, no problem. But after a certain age, suddenly the black one start picking up all the troubles, but the amber one age in a healthier way. Can you guys see that? Okay, so why I'm giving you this kind of example, because I know the math is kind of like, boring, but the math really is to model the data into different curve. Sooner or later, we're going to see a bunch of k value, theta value. I'll give you the data to fit and figure out how to hey, this set of data, what is the k value, what's the theta value, and then we need to compare orange with apple, doing risk accounting or survival accounting. Okay, and for insurance company, actually, that's what we're trying to do. Is that, hey, I'll charge you more at certain time or after a certain time. Why is that? You don't need doctor. You don't need to check with the mechanics when this car is young. But after a certain age, the cars become big troubles. Now let me ask you another questions. What do you think is the warranty these days? Do you think that all the car manufacturers give a lifetime warranty? So how they decide how long is the warranty is a reasonable time warranty for your car? So in other words, is that they figure out that if you're buying a Toyota, on average, what's the time you're going to trade in for another car? Okay? If it's 5 years, they make sure everything's fine within that 5-year warranty. After that, they will say, oh, do you want to keep your car for a little longer? We'll sell you a different rate of warranty. But certain car, okay, they know you trade in quick, or you always, keep the car forever, then the warranty will be in different rate. How do they decide that? Table or figure like this, okay? So can you visualize why we're doing what we're doing? Okay, So next example is called log normal distribution. Log normal distribution is not normal distribution, but once you take the time with a log, or whatever you're measuring with a log, it becomes normal distribution. Okay? I know Victoria can answer this one. How many of you know what is normal distribution? Normal distribution is based on what theorem? You have to know this. That should be common sense if you're a system engineer. Good job. Central limit theorem, and what is central limit theorem? What is central limit theorem? You should be able to do this without looking at, and I don't like Wikipedia's answer directly. Okay? Central limit theorem said that I don't care where you get your data from, but as long as you take the average or take the sum and then average it, the distribution, the shape will become normally distributed. Okay? And for, you know, I've done this every time, but let me do it again. Okay. We already done it the other day. Is that if I have a set of random number, okay, so this is uniformly distributed, and if I take this random number 10,000 times, okay, and if I take a histogram of this set of data, so data histogram, and from here to here, okay, and if you look at the distribution, it is very, insert a chart. Okay? So from 0 to 1, equal opportunity, right? You don't see a bell shape. However, okay, if you take the random number, and then let me just go to A, D, 10,000. And this time, all I need to do is now I have about 30 numbers, okay? So all I need you to do is take the average of all the random number, okay? And then if you take a histogram of the random set of average, okay, from AF1, no, AF1 to AF 10,000, and if you look at the histogram, insert histogram, what did you see? A bell shape. So please, in your job interview, when the ABET reviewer talked to you, what did you learn in statistics? You would say, I learned normal distribution. What's normal distribution? Mean and standard normal distribution. Mean is 0 and standard deviation equal to 1. Where did you use it? I used it for quality control and Lean Six Sigma. Oh, I'm going to be a big manager. That's fine. But if he asks you, so what the heck is a normal distribution? You should be able to say central limit theorem. That's the foundation. And what is central limit theorem? In job interview, you should immediately say, Oh, it's the power of average. I don't care. You can get a distribution from exponential, from gamma, from uniform, from any strange looking. You know, there's sine distribution, cosine distribution. There are all kinds of funky looking distribution. There are double peak distribution, you know, two bipolar distribution. I don't care where you get your distribution from. As long as you have a bunch of them, take the average. Guess what the shape of the average is going to look like? A bell shape. So central limit theorem in one sentence or in one phrase. What will be the phrase? The power of average. Okay? Visualize it, not memorize it. If you can see this, you know, you got a good degree here. Otherwise, we're in trouble. Okay, so for Thursday class, I'm going to start building more shape. And for Thursday, did I ask you guys turn in your homework today? Oh, okay, just the Excel. Okay, for Thursday, I would like to have some Google search. I'll find a Google search terms for you. And pay attention to your email, okay? And what will be the terms I'm interested in? What is central limit theorem? And what is gamma distribution? Okay? And last time I asked you gamma distribution, you know, where are you going to use it? This time I'm going to basically ask you, okay, look at gamma distribution, look at Weibull distribution, look at exponential distributions. I would like you to compare the shape and see when the parameter change, how the PDF and CDF change their shape. Okay? Yeah. See you Thursday, I guess.